Thank you for joining today's webinar, Solving 1000-Cell Electrochemical Battery Packs with JuliaSim. My name is Sanjeev Dasgupta, and I'm the Marketing Manager at JuliaHub. Today's webinar will be presented by Dr. Marc D. He is the lead developer for JuliaSim Batteries, and Dr. Christopher Rackauckas, VP of Modeling and Simulation at JuliaHub. During the webinar, in case you have any questions, you can type it in the Q&A section, and we'll answer it in the order it was received. Over to you, Marc.
Thank you for the introduction. So today I'm going to be talking about simulating 1000-cell electrochemical battery packs using JuliaSim batteries. So today is the first in a series of webinars. Today, of course, we're focusing on battery packs and those who build and integrate battery packs into systems. But we also have a few on the roster for March and April, which focus on looking at a deep dive in manufacturing defects that affect these OEMs that produce batteries, but also the users of batteries who care about quantifying the effects of these defects. And additionally, in April, we're going to take a comparative analysis of different chemistries using JuliaSim batteries and seeing if we can get the best battery for some particular use cases. So in the battery modeling world, there are a few challenges of modeling lithium-ion batteries. So there's this well-known issue in the industry that cell-to-cell variation is a major issue. But yet, if we look at the modeling tools that are available, we see that a lot of models are really designed as a one-size-fits-all approach. And we know it's really at odds with this kind of fundamental flaw in battery manufacturing. So there's another problem, which is that if we want really detailed electrochemical models that are accurate, they are traditionally very slow to simulate, so they take quite a long time to get results. They are additionally very difficult to solve in a robust manner, so they may break at high C rates or in different conditions. As well, they do not scale very well, especially to something like the pack level. So they're slow enough as it is at the cell, and going to the pack is just a huge level of difficulty that traditional tools and models just aren't able to really overcome. So if we take a look at the traditional and available tools that we have in the market, we can kind of subdivide them into two extremes. Those which focus on really accurate electrochemical cell models, which have very detailed behavior at the cell level, which is very accurate and involves systems of partial differential equations. But yet, this is ultimately a cell model, and that's where these kinds of models live. They live for the single cell, and they live maybe at a handful of cells that are connected together, but really, that's it. And on the other end of the extreme, we have empirical pack models that look at thousands of cells all connected together, but yet the models strip away all of the physics. They consider batteries to be very simple equivalent circuit or empirical-based models that lump them together as a series of resistors or capacitors that really gets away from a lot of the physical understanding that we have of these batteries. So with JuliaSim batteries, we want to merge these two extremes. We want to take detailed electrochemical cell models and bring them to the pack level. So you can get all the insight that we have from these electrochemical models at the level of thousands and thousands of cells in a real system or a real application. So with JuliaSim batteries, we start at the cell. We base these models on detailed electrochemical models, starting from the complex Doyle-Fuller-Newman, or DFN, sometimes referred to as the P2D model. And we go all the way to the little bit more basic single particle model and single particle model with electrolyte. So these PDEs are solved and discretized using the finite volume method, as well as a discontinuous Galerkin method. And if we compare the tool, JuliaSim batteries, to other tools that are in Python, as well as MATLAB, we see that given the exact same set of modeling equations, we're 100 times faster with less than 0.01% error. So we're solving the exact same physics, we get the same results, yet we're 100 times faster. So in addition, we have thermal and degradation submodels that you can use to assess the lifetime of your battery. And like we said, this is built really for the cell, and we can build it all the way up to a module. We can put it together in a pack, and it's easy to define parameter sets. And we have a few that are chosen for NMC, for LCO, as well as LFP chemistries. So one of the things that we showed at a previous webinar is this high-level performance at the cell. So in this example plot that we have over on the left, we're showing the results of a lifetime analysis using a DFN model with degradation and thermodynamics. So if we take a look at the actual real-time continuous cycling and discharging of this cell, we see that it lasts about 65 days, whereas the simulation time that we see using a JuliaHub cloud computing platform is only about 15 seconds or so, which is really nothing compared to the amount of time that we're simulating. So if we compare the real-time simulation of 65 days to the simulation time of 15 seconds, we get over a 100,000 times faster than real-time performance, which really greatly affects the kind of workflow that you have when using these tools. So to give a bit more deeper dive on the performance and the numerics behind JuliaSim batteries, Chris, if you like to take it from here.
Yep. Hello. Yeah, I'm Chris Rackauckas. So I'm VP of Modeling and Simulation here at JuliaHub. And we wanted to kind of give a bit of a deep dive into, some of the performance before we go into the demos, right? So we'll demo a 1,000 cell battery pack, and you'll see, what the kind of results that we can get with it. But before going to that, we kind of want to explain, what is some of the cool stuff that we're doing with JuliaSim in order to reach these performance levels, right? So on the next slide, the key idea behind this is that JuliaSim is an acausal component-based modeling framework. There's many reasons for an acausal component-based framework. So if you're familiar with, say, Modelica or Modeling Toolkit, these kinds of tools make it natural to build fairly large equation systems fairly fast, right? And the key here is that they have a lot of libraries and subsystems which you can use to be able to connect different kinds of components, right? So today we're talking about batteries, but you can also talk about mechanical systems, motors. You can talk about multi-body systems, and you can also talk about things like HVAC systems, right? So there's all sorts of different kinds of models that can be built inside of such a system like JuliaSim. But the key then that gives us this performance is kind of shown on the next slide, right? So what happens in this kind of modeling system is that we can get all of the equations, right? So for example, all of the equations associated with an electrical circuit, and then that's what's shown on the right. And then on the left is this automatically produced version that is a simplification of the system. So you can say, here's the 20 equations that describe the system. There's Kirchhoff's laws, there's this, there's that, there's this, there's that. But at the end of the day, it can find out that, hey, actually, I only need to solve one equation to know the answer to all 20, right? And so there's an automatic simplification system behind the scene that makes it so that way, even before you get to the numerics, you get some performance benefits. And as you know, there's a lot of good numerical tools within Julia. And so these symbolic tools then compound this performance benefit. On the next slide, then, the key feature that really made it so that way we can scale this to the pack level is the fact that we have a way to be able to do repeated structure optimizations, right? So if you have this kind of situation where you just happen to have some physical structure that is then repeated, for example, if you have cells in a battery, right? Then what we can do is we can actually take that and optimize on that structure. If you go to the next slide, what happens is that inside the compiler, it's able to hold on to the idea that every cell is supposed to be the same, and then do certain optimizations based off of the fact that it has this repeated structure within it. And so what ends up at the end of the day is this last piece where you can generate on the next slide, where you generate these loops from the combined code. But what you then see on the next slide there, though, is that the loops that you get can be actually different from the loops that you might have written down, right? Because, as I described, well, there's a simplification process behind that scenes. Where does that come into play for something like a P2D battery model? Well, things like boundary conditions can be canceled out automatically. You can solve these nonlinear systems and generate like pieces that then it automatically contain the boundary conditions without requiring these equations and all sorts of other tricks like that. So at the end of the day, you get a very fine, simple code to solve, and that is only a subset of your equations, but it knows how to reconstruct everything else from the subset. And then, so, if you're solving less equations, then you should be able to solve faster, right? So that's one of the key pieces involved in here. On the next slide, we show what then the results of this end up being, right? So the blue line on the left there, this is JuliaSim compiler with no loop. So this is without the loop optimizations. And you can see that by the time you get to, let's say, 20, 30 cells, the compile time is shooting out through the roof. The runtime is not even measurable at that point. It's just not a fast way to run this code. But with the whole JuliaSim compiler process, with all of these optimizations together, you can see that we're able to bring this all the way out with, this is SPM with the NMC chemistry. We're able to do 5,000 battery cells, compile the model within about 50 seconds, and then be able to run it quite quickly as well, right? So this shows that, that we have this kind of special system then that is allowing us to be able to go to the battery pack level. So next, then I'll pass it right back over to Mark, who's going to show one of these large scale battery pack simulations.
Yeah, so I just want to quickly pause before we get to the demo and see if there are any audience questions.
I see that there is a hand up. If you can put the question into the Q&A, that'd be great.
See a questions there. Maybe if somebody could read it out to me.
Yeah. So the use of the word acausal here is purely to distinguish from causal modeling, or does it have another meaning in this context? Yeah. So acausal in this context means differential algebraic equation modeling, where the semantics of the model are defined through connection semantics, not necessarily where those connections do not necessarily have to be inputs to outputs, right? So Simulink, for example, requires that you have defined on each of your physical components what your input is and what your output is, right? On the physical components of this system, it doesn't necessarily require you to define what an input or an output is. You just say a resistor is an object that has a current, it has a voltage, and it satisfies Ohm's law. And from that, it's able to then, once you give it all the other equations, it can actually generate the input-output form through the symbolic piece. So it distinguishes it from causal modeling like Simulink. So besides cloud compute capabilities, what else does JuliaHub offer? Meaning, are there loop rerolling optimizations at compiler level in the base open source version of Julia? No. So the open source version of the modeling system is Modeling Toolkit. It's fully capable for describing and building all these models, but the loop rerolling optimizations and some other optimizations I didn't go into, things like linear system optimizations that are used for multi-body systems. These are proprietary to the JuliaSim compiler. So you can use the open source modeling system, Modeling Toolkit, to make any of these models. Though for running them in the fastest way, you will need the extensions of the JuliaSim compiler. Let's see. So I guess this might be a good question to Mark. How is JuliaSim Batteries different from other battery modeling tools like PyBAM?
Yeah, so in terms of the actual models that we have, they're very similar. So they focus on a similar set of electrochemical models, mainly the DFN, but also these like single particle type models. A big difference is in the robustness of them. So we focused really strongly on making sure that JuliaSim batteries can simulate robustly for any series of operating conditions. We perform tests that go all the way up to 100 C for charging and discharging. We can do that very quickly. Additionally, we focus a lot on these numeric aspects. So things like JuliaSim compiler and things like this like finite volume method and Galerkin discretization. These all really add up to give a basically 100 times faster performance while still solving the same set of equations.
All right, thank you. There's one question here, which is why does the simulation time increase at 3,000 cells and then decrease afterwards? That's the compile time, and that's just because that's where the GC actually had a clean of the system. So it's not a major factor. It's kind of due to the fact that the benchmark was running them in series, and that's where the garbage collection decided to probably run. I wouldn't take note of that blip as like a special point. So for this pack simulation, what's the difference between these cells in series? Are they at different temperatures or slightly different capacities? Mark, you want to take that one?
Yeah, so for this example, I believe these are all identical. But even if they did have slight variations, this doesn't affect the performance really or it shouldn't affect it too much. So what we're seeing on the left-hand side is this like compile time. That's really independent of something like, changing some of the parameters and whatnot.
Yeah, and the next webinar will go into the manufacturing defects and showing the creation of these batteries with the uncertainty and changes in parameters. So but the performance doesn't change for that case. It's really just an interface change in the way that you use it. So, but we'll go in a bit more into that case in the next webinar. And will you show the NFD model of do you use volume averaging, homogenization to convert it into 1D? Mark, you want to take this one?
Sorry, the what model?
Will you show the NFD model? Volume averaging. I think that these are the lumped parameter models. The models that we're showing talking about here are the more larger PDE models, right?
Yeah, I'm not familiar with NFD. Maybe they mean DFN model.
Oh, yeah, I think he means a Dufour-Newman. Yeah, DFN. That looks like a typo. Yeah.
Good question.
Yeah. I mean, yeah. So the compile scaling with the DFN is similar to this one, but yeah, we don't have a slide prepared on that. So if you're interested, you can get in contact with us, and we can put together a slide and such on that. But for this one, we just wanted to show one slide of the performance, just as a quick summary.
Yeah, so I think to answer the question about DFN, I think it's just it's a P2D model. So we have 1D in the X direction across the length of the cell, and we have this R direction inside both of the electrodes particles. And there's no like volume averaging tricks that we do to improve the speeds. Okay, I think we should maybe move on to.
Well, let's try one more. Let's try one more. And then so does JuliaSim model allow for replacing models with different cell types or different packing formats?
So you can change the different cell chemistry. At this point, we don't change too much of like the cell geometry. So comparing from like a cylindrical cell to a pouch cell. If there are other like thermal aspects, we can model these with things like lump thermal analyses or including electrical resistors that may include some effects. So there are other ways to include these kinds of effects in the battery models.
All right, cool. Yeah, so there's still a few more in the list. Well, we can move on and take those at the end. So yeah, let's go on to Mark's next part, which will be going into the demonstration.
Okay, so I'm going to be demonstrating again this 1,000 cell battery pack with JuliaSim batteries. So to give an example, let's say we're trying to scale up from a single cell all the way to the pack. So we want to take this prototype 1,000 cell battery with 25 in series and 40 in parallel. And we want to look at different CCCV fast charging strategies until we reach end of life of 80%. So we know that from our manufacturer that we're going to receive a batch of cells which have slight variations in the cells due to manufacturing defects. So the first set of variations is 1% standard deviation in the electrodes and the separator thicknesses. So this is a little bit less than around 1 micron for each of these, as well as we have 1% variation in both of the electrode active materials. So all in all, pretty small levels of variations in all of our systems. So let me quickly jump to the demo. So with JuliaSim batteries, we start at the cell. And here's where we're going to start for our system. So the way that we load a cell is we specify first the type of model that we have, as well as the set of chemistry parameters that we're using. For this example, we're going to run it isothermally and with SCI degradation turned off. But later, we're going to show the results and the time for running it with these modes turned on. So like I said, we start at the cell, and the way that we build up from a pack, like we have here, is we specify some level of connection. So here, the only difference is that we're using a model which is more appropriate for this level of scale. We're using the SPM level model. And we're specifying these batteries as 25 in series and 40 in parallel. So the way that we actually run these experiments is we can say charge it at some C rate, and we can hold it at our maximum voltage until we reach some minimum current. And these are all defined based on our set of parameters for NMC chemistry. And from there, we can simulate our pack level performance. So we do have impacts of defects on our pack. But if we take a look at this plot over here, this is looking at the cell level behavior for the voltage. If we have 0% defects and a C/2 charge rate. So if you look at this plot, it looks very similar to what you would see for really a very standard level charge or CCCV charge of a battery pack or a battery cell, if there was really nothing complicated that was going on. And really that's the reason that we see this is that because there is no defects in this battery pack right now, there is little variation. So if we bump it up to 1% variation in the thicknesses and the active materials, now we can start to see some of the defect behavior and some of the variation on our performance that we get for our system. So you see this at the CCCV region. You see a little bit of an increase in the uncertainty once we enter CV. So if we change it from a C/2 C rate to a 5C charge rate, we can see this effect gets a little bit more noticeable with our voltage. So every time I change one of the sliders here, I click a different C rate or a new deviation on the thicknesses and active materials, it generates a completely new simulation. So in the simulation, we're simulating 1,000 connected PDE models for the pack using the SPM. So if I change this plot over to the C rate, what looks like just a minor variation in the voltage, you see now becomes a much greater variation for the C rate and the current of all these various cells. And this is only for a deviation of 1% based on these specifications. If we bump this up all the way to 2%, we see an even greater difference. So this is, once it loads, it's about double the amplitude that we had for the previous case. And this is just including really minor defects in the manufacturing process that we throw all the way throughout the rest of the simulation. So we don't just have to look at a distribution of all the cells in the pack. we can look at every single individual cell and see the complicated behavior that arises. So if we click this box to show all the individual cells, now because we are truly simulating all the cells in the pack, we can see what happens at every point in the pack for every cell and its complicated behavior for this system. So we can change our plot to look at all these kinds of metrics like power, as well as state of charge for a system. And we see that we get, even from a very small deviation in the defects, a pretty complicated behavior for our overall system. So this is just one single cycle that I'm showing you. And if I jump over to the slide deck, we can also consider this over the length of the entire life cycle of the battery pack. And this can be done for different C rates, as well as for including these degradation modes and thermal modes in our pack and in our cells. So the goal here was trying to find what happens when we charge it at different C rates. And we see once we reach this 80% state of health criteria or end of life criteria, we get a reasonable result, which is those that are charged more quickly reach end of life much more quickly than those that are charged slowly. But we also see this interesting distribution that we get for all the cells in our pack at end of life. So if we plot the distribution of each cell's SOH, once we reach this end of life criteria, we see that those which are charged much more rapidly have a much more narrow distribution in the end of life, whereas those that are charged more slowly have a much more wide distribution. And that seems to be replicatable across the various C rates that we've tried. So if we look at the 1% criteria for the 1C charge, we get that 1% of the cells reach end of life at cycle 826. The median reach it at 899, and the 99th percentile reach end of life at 991 cycles. So between the difference of the 1% compared to the 99%, there's almost a 200 cycle difference here. So something like this can have a really significant impact on what you use these cells for, as well as something like the maintenance or the various aspects of how you treat this battery and what kind of conditions you want to put them in based on the various defects that have been specified to you. So for each of these simulations, it took about 30 seconds per cycle to get the entire simulation when averaged out. But again, these were run on JuliaHub. So these can be run in a parallel environment, which means we got all these simulations run simultaneously. So you don't have to wait days upon days to get these results. So like I said, even within the same pack, we see pretty major differences that each cells have. And this is really a result of running this analysis for the entire end of life cycle with JuliaSim batteries. So one question that is natural to ask as a result of these different distributions at end of life is, why is this the case? Why do different C rates cause such a wide and changing distribution for end of life behavior? So because with JuliaSim batteries, we truly simulate every single cycle and every cell at every cycle, we can investigate root causes like what is causing this variation. So what we have in the plot over on the left is the cycle 899 of the 1C charge, which is the cycle in which the median cell reached end of life. And the color axis that we have indicates the SOH for this pack at its end of life. So those that are blue, they have a much longer lasting cell. And those that are red, those are overcharged compared to the 80% criteria. So we can see we get a pretty nice trend based on the C rate plot where those that are charged a little bit less aggressively, those that are blue on the top, they have a longer state of health or a greater state of health at end of life. Compared to those at the bottom of the plot, those which are overcharged, that seem to be getting a much less capacity in this pack. So this doesn't really necessarily address the question of the distribution. So we can take a look at another charge rate, the 3C charge rate, and that its end of life. So what we see is a very similar trend in the plots where those that are underutilized reach a greater state of health. But what we can analyze from this plot is that those which are charged less quickly, such as the 1C, they have a greater region of current imbalancing. In the CC region, they have this much longer region where the currents are imbalanced compared to the CV region where they're pretty uniform. And comparing this time in the CC region compared to the 3C plot, we get nearly threefold reduction in the total time. So if we take this one-to-one comparison between the various plots, we get a pretty clear answer for why this distribution occurs for these various C rates. And the reason is just that we can compare very quickly the plots that we get for the C rates at various cycles. And answering a question like this, that is really a pretty challenging question to take on, which has a big impact on the way that you use and design these packs, is really pretty easy with JuliaSim batteries. So with this seminar, one thing that we really showed throughout this presentation is how you can really seamlessly scale cells from the single cell, the detailed electrochemical, all the way to the pack level, and how you can get great performance all throughout this simulation process. And this is really built upon JuliaSim compiler, which gives you state-of-the-art performance going all the way from the cell level to the pack level. And once you're at the pack level, you can very quickly investigate complex behaviors that arise from this pack, such as the lifetime analysis under different C rates. So one thing that we want to really focus on is building JuliaSim batteries and getting it to work for your use case. So we want to propose a short-term engagement to really optimize and finely tune JuliaSim batteries for you. So like we said, we build JuliaSim batteries starting at the cell level, and we extend it all the way to the pack level. So we can work with you to take your chemistry, your data, build cell level models and scale that all the way to packs. We can use your specific charge and discharge protocols using validated models, and really get something that works for you and for everybody on your team. So in addition, we can provide training and documentation on using JuliaSim batteries, as well as the rest of JuliaSim. And we can provide the capability to just generate custom reports as a result of these simulations. So like I said, all this is done on the JuliaHub cloud computing environment. And as a part of this process, we can provide dedicated cloud compute with JuliaHub that's fulfills SOC 2 compliancy, and we can provide this test bench as a part of the engagement. So if you're interested in any of this, please contact sales@juliahub.com. So to give you a sneak peek at a few of the things that we're going to be showing in the next webinar and at the conferences we'll be attending, we have this graphical user interface that we're developing specifically for JuliaSim batteries. So this is designed for those people who don't necessarily want to be in the code, who want to use it at a more high-level interface that makes sense for their background, for their understanding of batteries as a battery engineer, as a battery scientist. So you can work with your team on integrating these detailed and performant models at the cell or the pack level into wider system level models. So in the next few weeks, we'll be at the International Battery Seminar, where we'll be showcasing this graphical user interface. So we have a booth number 1005. If you're interested and you want to talk to us at the conference, feel free to stop by and we'll be happy to chat and show you JuliaSim batteries. So with that, thank you for your attention, and I'm happy to take any questions.
Hey, Mark. So a number of questions I see in the chat. Does our model work only for cylindrical cells? How about sort of pouch plate?
Yeah, so I talked about this a little at the previous part. So this is more independent of the like overarching geometry. It should work just fine for pouch cells or for cylindrical cells. There could be slight differences or differences that you get in the thermals and maybe some electrical resistance, and these can be modeled using lumped thermal or lumped electrical resistors or capacitors and whatnot inside this like acausaling model framework.
Cool. And could you, can we sort of model 2D and 3D? Do we provide 2D and 3D models as well? And could you also comment on adding current collectors to our models?
Yeah, so on current collectors, we already have current collectors. So those are just built into the model and can be used. For 3D, so right now in particles, well, throughout the cell, we have a P2D model. So we have 1D across the length of the cell. We have 1D inside the particles. At this point in time, we don't have 3D or 2D in any of these regions. But if that's something that interests you, feel free to reach out.
And so let's say we built this model, right? And let's say we built a model of a battery pack. What sort of operational sort of battery performance KPIs can we compute from this model?
Yeah, so you can compute things like the lifetime. You can look at things like what is the estimated warranty based on my specific defects that I have from my batch. You can look at things like efficiencies. Yeah, there's a whole list of metrics and observables that you can get for a pack or for a cell as well.
Right. And do we also support, in addition to, let's say, lithium ion, do we also support sodium ion at this moment, or other types of chemistries like that?
Yeah, so at this point, we don't support sodium ion. We're actively working on supporting lithium metal though, and as well as like silicon-based electrodes. So we're not just thinking about the current day state of the art for batteries. We're thinking in the future too, and how we can model these and get the same performance for these kinds of systems as well.
And just for the demo that we showed just now, what kind of degradation model were we using in the demo?
So we were using an SCI capacity faded model on the anode.
Could you also comment on whether we can use these models for electrochemical metal refining?
Metal refining, electrochemical metal defining? Not quite sure I understand the question.
Yeah, so if the participant could sort of elaborate on that in the Q&A section, that will help. But I do do have another question on if you are integrating a new chemistry into the model, like let's say silicon anode, how easy and quick is it? What is the process basically? How would we integrate silicon anodes into our model?
Yeah, so I mean, silicon is a tricky one because with silicon you have expansion, and that's not quite so easy as say like jumping from NMC cathode to an LCO cathode. There is like a decent amount of complexity that goes into modeling expansion, but it's something that we're actively working on, and we're working on making it easy and flexible to do this. But it is still a work in progress.
So, what about lithium plating? Can we model that in JuliaSim?
Yeah, so I mean, certainly lithium plating, it's not currently in JuliaSim batteries, but it's easy enough to add in, and yeah, it's on the roadmap essentially.
Okay, and does the software currently support modeling half cells?
Yeah, it does.
Perfect. And one, yeah, we have more questions, but well, besides the chemistry, battery cell microstructures degrade over many charge cycles. So can structural degradation such as micro cracks, metallic whiskers, anode pitting be added into the model?
Yeah, so there are models for things like cracking of the electrode particles that go on in over the course of like lithium ion battery cycling. I'm not so familiar with other types of or the other models that they mentioned at that scale, or like the P2D or the SPM scale. I would have to look into that more to really address that.
Yeah, and one of the things that we are developing throughout JuliaSim, right? It's a scientific machine learning enabled modeling and simulation engine. We are looking at having some machine learned degradation models, so that way they can be, added to models using a user's data. So if you're interested in these kinds of applications where you need something at like the pseudo 2D level because you want to scale it to a pack, but you have data for how your system is degrading, we have ways to be able to learn more effective or more accurate degradation models for these cases. And so we'd be happy to talk with you in more detail. That'd be a great conversation for a follow-up.
Yeah, and I think the participant clarified what they mean by electrochemical refining. So electrochemical refining uses a series of cells to electrolytically dissolve and deposit metal ions onto plates to concentrate the target metal. Is that something that we currently think about while building this library?
Yeah, I think it's, if you wanted to use JuliaSim batteries as like the voltage source to run this kind of thing, yeah, I think it could definitely support it. I mean, it's built to be flexible, so if you define some pack or some module or some connection of cells, you can use it really for a wide range of use cases.
Yeah. Thank you. Are there any other questions? I think we've answered everyone's question thus far.
Maybe we can wait for a couple of minutes to see if any questions come in. Okay, I see no other questions coming in. Should we call it a day today?
I think
Yes.
that was great.
Yeah.
Yeah, thank you everyone for your great questions. That was very deep, and it seems like a lot of people have a lot of questions to ask. Please get in touch with us. If you contact sales@juliahub.com, we'd be happy to have a personal one-on-one with you or your company and go into more detail. Kind of showcase a bit more of this. And again, if anyone wants to come talk with us, if you're going to be at the International Battery Seminar down in Orlando, we'll also be there. We'll be in booth 1005, and we'll be there to chat with anyone. Will we see invitations for follow-up webinars? I believe so. If you're on our mailing list, so do make sure that you sign up for the JuliaHub mailing list, which should give the information on the next one.
Yeah, thank you so much.
Right. All right. Thank you, everyone. Thank you for joining today, and thank you, Mark. Thank you, Chris and Ranjan, for this wonderful webinar. And we hope to see you in our other webinars as well. The recording of this webinar will be shared with you over an email so that you can view it whenever you want at your convenience. Thank you again, and we hope to see you in the future as well. Have a great day. See you.